we defined what work is. We said work is simply the product of force times distance. And the force has to be parallel to the distance that we are covering. Yeah, and we also said even negative forces like friction are also going to be doing work. That's what we said. So if I give you a box being pulled in two opposite directions like this, there's a force this side. Let's say there's a 100 Newton force and there's a 20 Newton force this side. Then the distance that we are dragging this before we stop dragging it is, let's say, 5 meters. Then I ask you for the work, the overall work done on this object. You simply get the work done by 100 newtons in this 5 meters. So it's going to be 500, right? The work done by this guy is going to be a 500, which is Newton meter. Those are the units for work. This side, the work will be 20 by 5, which is simply going to be 100 Newton meter. Then the overall work, the net work, is simply going to be the bigger work, the positive work, minus the smaller work, which is simply this work here, to give you a 400, right? It's the same as you just getting 100 minus 20, giving us 80. So the net force is simply 80, then multiply it by 5. So which is the distance what we are having is still going to give you what? Your net force, which is 80 newtons, is going to give us the net work. Yeah, so we defined what work is, and we also said apart from our work, we also have energy, and there are two most important type of energies that you need to know. We talked about kinetic energy, which is energy due to motion, and we also discussed potential energy, the energy due to height or position of something. Yeah, so here we say this is simply potential energy. This is what we have. And we said there's a relation, there's what we call work energy theorem. The relation between work and energy is that work is simply the change in kinetic energy plus the changes in the potential energy. That's what we said. And I emphasize to say potential energy is always taken to be 0 because whenever kinetic energy is involved, your object is moving in the horizontal line. In the horizontal line, there is no movement in terms of there's no height, right? It's just moving in a flat straight line. So we cannot have potential energy if something is moving on the x-axis. Yeah, because height has to be in the y-axis. So no wonder potential energy is 0. So we are literally just saying that potential energy is equal to the change in kinetic energy. By change, hope by now you know, we just mean the final kinetic energy, the one we get by final velocity v, minus the initial kinetic energy, which is half m, then u squared. This is what we have. Yeah, so this is what we said in terms of the work energy theorem. And lastly, we discussed something to do with power. We said in layman's terms, we said power is simply the ability to do work. That's what we discussed. Yeah, so the ability to do work is, the rate of doing work, that's what we call power. So power is dependent on the work. So we just said P is equal to the work done over time. And we can say the power is equal to the work done. Work done is simply the same as what? Force times distance, right? Over time. Now you learned to say velocity or speed is equal to distance over time. So meaning F d over t, this can be replaced by v. So some books will give you as power is equal to force times velocity or speed. So some people also use this. So it depends with what you are given in a question. That is what is going to determine the formula that you are supposed to use. So this is just a recap of what we did last time. Now today, I specifically want to look at examples like I promised. We're going to look at examples of work, energy, and power, and we're going to start with the first example. So let me just start with this. I'll just run you through this. These are very simple, straightforward example, until maybe the last one is the one that will be a bit challenging because it's coupled with a bit of some Newton's laws. So something on the incline, you'll see it when friction is involved and everything else. So I also mentioned, don't forget the part I mentioned to say, whenever work is being done by friction, work can also be written as negative. You can get negative work if work is done by friction. So friction is a force times the distance. Yeah, so if I give you a box, not just friction, I give you a box, pull it in the opposite direction by 20 newtons, the distance is 8 meters. What is the work here done? The work is going to be negative 20 times 8 meters. This is Newton, so the answer will be negative 160 Newton meter. It's possible. Why? Because work is a vector, so meaning it has both magnitude and direction, meaning it can either be positive or negative. It depends on the force, because work is a product of a scalar and a vector. No wonder it's a vector, because force times the distance. So the direction will depend with respect to, depend on the force. So if the force is negative, meaning the work will also be negative. Yeah, that's basically what this makes sense, because if you're dragging something, meaning you're slowing it down, you want it to come to a stop. So you're going in the negative direction. Yeah, so this should make sense to you. Hope this is okay, guys. That's what we were doing last time. Now we're just doing examples. So example one says a force of 3 newtons acts through a distance of 12 meters in the same direction of the force. Find the work done. This is pretty straightforward. Now, please bear with us why they're using the cos theta, because I said sometimes the force can be given at an angle, right? Like this, at an angle like this, meaning you have to resolve this force to give you what? F cos theta and also F sin theta. To find the work, you just say the work is equal to this force times the distance. So that's why you're having the force, F cos theta, then times S, the distance S. So this is what is giving us the Fs cos theta. Now it doesn't matter whether the force is not related to any angle. So if a force is in the horizontal already, if a force is here, a force is already given here. The force here is 3 newtons. The distance we have moved is what? 12 meters, right? So here we'll just go direct. You can decide to use 0 or 360. It's up to you. If you want to consider an angle, because it's on the line, right? So you just say work is equal to force times distance. The force is 3 newtons. The distance is 12 meters. So when you multiply this, that's how we're getting the what? The 36 joules or Newton meter. That's what you have. Yeah, so it's okay even if you do this. So hope you're not surprised where the cos 0 is coming from, because if a vector is on the x-axis, if it's here, the angle is taken to be 0 degrees or either 360. Either way, you get the same answer, because cos 0 is a 1. Yeah, so it's as good as you just saying 3 times 12 independently. Christopher, Mitty, are you getting this? Is this okay, guys? This should just be revision, this type of question. Is this okay? Okay, so if this is okay, we can move on to the second one, so that at least we go to hard stuff. Here they are saying the same thing. An object is being pulled along the ground by 70 at directed at 28 above the horizontal, so 75, 28. So we are having the force here is 75 newtons. The angle is 28 degrees. And the distance that we are using, that we've covered, is 8 meters. That's what you have. So now we are interested in getting the work done. So work should be with respect to the force parallel to the distance. So we resolve the force into the x component, which is Fx is equal to, you say your 75 newtons, then you say your cos 28 degrees. Of course you have your y, but we have no use for the y because there is no friction or whatsoever. So the 78 newtons, then sine 28. Then from here we're just going to straight away get the work, because the force, the x component of the force, is in the positive direction. So we're simply going to get this force and multiply it with 8 meters. So I'll rather start with 8 meters so that you are able to punch the 75 newtons, then cos 28. So if we punch this, you should be getting something like this. This is what you should be getting. So if you punch it, you should get a 530 or a 529.9. Then you round it off. We put it to the nearest tens. So this is what you're going to get. Yeah, so similar to the next one where there's friction now. So before we even see the answer, let's see the question first. They're saying a 0.3 kg object slides 0.8 meters along the horizontal table. How much work is done overcoming friction between the object and the table if the coefficient of friction is 0.2? I mean 0.20, that's a coefficient, that's our mu, right? Yeah, so it's important in physics, it's always important to draw your free body diagram. So you just say your FBD, your free body diagram. This always helps you visualize what's happening. So the mass of this guy, the mass is 0.3 kg. That's what you have. So I'll take my G gravity to be 9.8 if we ever need to use it. Yeah, because this thing is moving on a surface and it's covering a very short distance, which is what the distance is 0.2 if I'm not 0.8. Okay, so 0.8. It's the coefficient of friction, which is 0.2. That then they're saying this is what you're having, right? So there's no other force that is being used to pull this thing. Now we're just trying to overcome friction, meaning the friction that is happening here is happening in the opposite direction. That's the friction force. That's the only force. There's no other force that they've mentioned here. Is there? It slides along the horizontal table. How much work is done overcoming friction? So it wants to stop, meaning we're not applying any force on it. The only force acting on it is friction. That's what they mean, until it actually stops and it takes this distance. So we know we should have a normal force there, which is equal to the weight down according to our Newton's laws. There's mg. We know to say the normal force is equal to mg. So the you have what? The 0.2. I mean the mass, sorry, the 0.3. The mass is 0.3. Then multiplied by, okay, so to make my math easy, because I don't have a calculator, I'll use 10 as g so that I can just get proper number. This will be 3 newtons. That's the normal force. Now, once you get this as your normal force, you can now get the frictional. The frictional force is mu times the normal force. So I hope you remember this. The coefficient of friction here is 0.2. We multiply it by 3. That's going to give us 0.6 if I'm not mistaken. This is going to be a frictional force. So the work done by friction is going to be negative times the distance is negative 0.6 times the distance we are covering is 0.8. So this is going to give us what? This is going to give us, we have what? 36 plus this is 48 if I'm not mistaken. Yeah, this is going to be 0.48 joules. That's what you should get, something close to this. I think so. This is going to be the case or something like that. So you get your friction of that, then you multiply it by our distance. Yeah, so here they are getting 0.4747 because they are using 9.8 as their gravitational acceleration. You notice here the g they used is 9.8. I used a 10 because I didn't know that I got a 3. My normal force was 3, not 2.9. Yeah, but the process is the same. You were just supposed to use g as 9.8. I was avoiding that because I'm not having a calculator, so this is what you'd get. Any questions here, guys? Is this okay? Okay, so Betha, are you listening what we are doing here? Are you following, Madam Betha? Okay, so this is when friction is involved. We're getting the answer to be negative because the only force acting on the object is friction, and friction always goes in the opposite direction, which is in the negative. in this case, yeah, so let me not say it goes in the negative, because there are cases when it can go in the positive, yeah, like on the incline. So now the next example, so here they're saying how much work is done against gravity in lifting a 3 kg object through a distance of 0.4. That's the height. So you have something here down, you're trying to lift it up, right? The only force that you're going to be working against is its weight, right? So weight is equal to mg. So again, because I don't have a calculator, I'll use 10 as my g. The mass is 3, so 3 times 10, that's going to be 30. So the force that you're countering is what? Is 30. The distance you're having is what? Is this guy here, 0.4. So the work done is simply going to be the 30. Then they got 29.4 because they used 9.8. Hope you're able to see. Then I'll multiply this by my 0.4. The distance that you're having. So if you multiply this, this is going to give us what? Initially, maybe here I'm getting a 12. Yeah, I'm getting a 12 Newton meter or 12 joules. That's the work that I'm supposed to get. And it's in the positive direction because we are lifting it up. Yeah, so you would get this if you use 9.8. Daniel, are you able to see what we have? Okay. Yeah, so this is on work. Then on energy, they've given us this here. So here they're trying to, I'll not talk about the relation of energy and momentum. This will come later on. It will come at the beginning of momentum. That's why we're going to talk about the relation between energy and momentum. We're just saying kinetic energy, to be precise, is simply half mass the velocity squared. Now it can either be initial kinetic energy or final kinetic energy, depending on the velocity that you are using. And we also have gravitational potential energy, which is simply given like this. This is mgh, depends on the height. So look at this guy here, this example here. They're saying a 2 kg mass falls through a distance of 5. So it was at a height, right? It falls, meaning something was above, right? This distance is in the y-axis. It's a height. So we are somewhere here. You need to picture it. So this 2 kg object is somewhere here. Yeah, this is the 2 kg guy. It falls through a distance. So let's assume this whole distance is 4.0 meters. That's what you have. And they're asking us how much work is done on it by gravitational force. So gravitational force is simply going to be with respect to the weight. Whenever it's something has to do with gravitational force, that's not that I'm mentioning about. They're talking about the weight. When you go on a scale, what we're just measuring is the force of gravity on you with respect to your mass, right? That's what we just want to measure. So according to this, we'll get the weight. The weight of this guy is, I'll just use my G to be 10. I'll use 10. So meaning our weight is going to be a 20. That's going to be my weight. Then if I have a weight for 20, I can multiply it with the total distance I'll get there. Remember the work energy theorem. We said what? We said work sometimes, it depends. Work is equal to, depends on what you are given. Work is equal to the changes in kinetic energy plus the changes in potential energy. And if something is falling down like this, there is no kinetic energy mentioned, meaning this will be a 0. The only changes you are seeing there is the potential energy, the mgh. So no wonder we're just using the mass, which is a 2. Then I'm using 110. Then the height is 4. That's how I'm landing to get what I'm getting, 80 Newton meter, or rather just 80 joules, and it's in the it's going down where G is positive, so the work also be positive. But because they're using 9.8, no wonder the answer is this. Yeah, that's what they're getting. Yeah, so hope this makes sense to you. And also, is there a second but here they're asking another question here to say, how much gravitational potential energy did it lose? It's the same amount. they are saying how it lost it. This part here when they're saying, did it lose? They are adding it because it's falling down, meaning it's losing its ability to fall down. Its energy, its potential energy is being reduced. And that potential energy was 80 joules, or rather 78 if you use 9.8. If your phone is on the floor, it cannot fall, right? It cannot fall down. It doesn't have potential energy. So we're just saying if the phone that was 4 meters above the ground had what energy? It had a potential energy of 78.4. This is the work that it was able to do after falling for 4 meters. Once it's down here, it cannot fall any further, right? It has no potential energy. Something on the ground cannot fall, right? It's just logical that it can't fall because there's no distance. It's already in contact with the ground. Yeah, so the same value we got for work will be the same value we get for potential energy because of this equation here. So work can actually be equal to the potential energy. Yeah, so that's what you have. Then we have the next one. Let me just work energy theorem. So here is what you have. This is a normal practical question. For those that are doing physics 1010, I will try to make a separate session because your questions are a bit interesting from your tutorial sheet. In as much as you do already have the solutions that I once shared in the group, it's okay that we go through it because the questions from the tutorial sheets are very confusing. The concept might be simple, but application is where the challenge comes in. So here is a question they are saying: a 0.5 kg block slides across a table with an initial velocity of 0.2 meters per second, comes to rest at a distance of 0.7 meters. Find the average frictional force that retardates its motion. So already they're telling us that there's friction involved, right? That's what they are telling us. Now, there is a key thing that these notes give us here. They are saying the work done is simply equal to the change in kinetic energy, to be specific. So if I may write the data that we have. Yeah, so the data that we are having, we need to write it nicely. So the mass is 0.5. Okay, so the mass is 0.5 kg. Then the initial velocity is 0.2, so you have 0.2 meters per second. The final velocity, this thing is coming to rest, so the final velocity is 0. The distance that it covers is 0.7 meters. That's the distance that we're having, S or D. Then they're asking for the frictional force. They're saying find the average frictional force that retardates its motion. What force is making it to come to a stop? That's what we're interested in. The only force that can cause something to completely come to a stop is simply frictional force. That's what we are implying. And the work energy theorem is going to be redefined now. We're just going to say this work that we're interested in is simply done by friction, and it's supposed to be what? Negative, right? And the distance that you have. Then the kinetic energy is just going to be the final kinetic energy minus the initial kinetic energy. That's what we mean by change in kinetic energy. Then we do our replacements. We don't have the F, that's what we're looking for, the frictional force. The distance we do have, it's 0.7. And this side, the final velocity is 0. So this whole thing becomes a 0 minus, there's half, the mass is 0.5, the velocity is 0.2. Okay, so 0.2 squared. Okay, so so the velocity is 0.2, and from here we're going to have negative 0.7 Fk. This is equal to this side. We're going to get a negative. This is also 0.5, so that's the same as 1/4. Then we have 0.2 squared. The negatives can go away. Then I can divide both sides by 0.7, even this side by 0.7. In short, we're just saying the frictional force is equal to, you can say 0.5 times 0.5 then times 0.2 squared divided by 0.7. Yeah, and if we punch this, let me just, yeah, so if we punch this, we are having 0.5 times 0.5 times 0.2 times 0.2, this whole thing, then divided by 0.7. So the answer I'm getting is 0.014114, 0.0114 Newton. So this is the force that we're actually interested in. Let's see, something close to that. That should be our answer. So yeah, you notice the answer is the same. However we do it, the outcome, you notice that is this guy here. This is how we're supposed to do such a question. Betha, is this okay? Any questions, guys, up to this point? Is this okay or it's confusing? It's fine. Okay, Christopher. If Christopher says it's fine, meaning it's fine. Because meaning could be a network problem, little Christopher. Oh, okay. I'll send the recordings to you. Yeah, because you need this before momentum. Yeah, so this is how we're supposed to do it, just using the work energy theorem. So the key thing to physics, guys, is for you to be able, as long as you identify the data from the question, which is easy to do, just write it out. Like here, they're simply telling us, before you even look at the method they've used here, look at this guy here. They're saying the coefficient of friction between a 900 kilogram car and the pavement is 0.8. So the mass of the car has been given, that's 900 kilograms. The coefficient of friction is 0.8. And the car, if the car is moving at 25 meters per second along the level pavement, when it begins to skid, to stop, so meaning the initial velocity u is 25 meters per second, and the final velocity when it stops is going to be 0, right? That's what we have. How far will it go before stopping? So how far means that's distance. What distance is it going to cover before it completely comes to a stop? That's what we're interested in. So imagine this to be like your Newton's case. You have what? So it's braking. There's no other force that has been mentioned. We just know to say it's coming to a stop. So the only force acting on it is what? Friction. But we also learn to say whenever friction is not given, but we have the coefficient of friction, we can always get it, because the normal force is always going to be equal to the weight in a case like this where there are no other forces in the y-axis. So the normal force, I'll just use 10 as well as my g here to make life easy. So we're just going to get a 900 then times 10. That's going to give us a 9,000 as your normal force, newtons. Then you know what friction is. Friction is simply equal to the coefficient of friction times the normal force. So the coefficient of friction is 0.8. Then we multiply this to be a 9,000. This is going to be, if you multiply this, that's going to be what? Is it a 72 or something? That's going to be, okay, let me say 8 times 8 is 64. 64 by 64 plus 8, that's 72 here. So this is going to be a 7200. So this will be the frictional force. This is what you get as a frictional force. Now, if we have the frictional force, remember they're asking for the distance, right, before it actually stops. Yeah, so we do have our frictional force. That's what we're having. Then they're saying if the car is moving at this, then it comes to a stop. We know, as we know to say there's a change, we have learned to say work done is equal to the change in kinetic energy, and the frictional force is 7,200. You do have this negative 7,200. The distance is what we don't know. The changes in kinetic energy. So we are supposed to always write something like this. But then to shorten this, I'll just write half, because mass and half are common here, right? And I'll just write something like this. This is what you get. Then from here, we're simply going to replace. So someone would have actually worked out this without including mass, because you know to say frictional force, we said, is equal to what? Mu times the normal force, which is mg. So someone would have just said the work done by friction, this is friction, times the distance is equal to the changes in the kinetic energy. So someone would have written something like this, and they would have cancelled the m, the mass, just cancel the mass there, and divided by mu and g. So even this side we can divide by mu and g, and then this will just give you your distance. So distance will be, there's a half, the final velocity is 0. We are coming from a velocity of 25. So this is 25 squared, then over negative, the mu here is 0.8, and the g I'm using 10. Yeah, so this should give us something like a 0.5 multiplying negative, this should be 625, then down we just have negative 8, and this is going to be, let me see here, so we're having a 25 by 25, that's 625, then by a 0.5, that's going to be 312, then divided by 8. Okay, that's a 39, approximately a 40. So this is a 39, approximately. So is it? No, not a 14, because this guy cannot give, right? So yeah, so it's just 39.06. Yeah. So this is roughly what we have done. We've just used the fact that the work done is equal to the changes in kinetic energy, and then the work that was being done here, the force that was responsible for that was friction, and the work done by friction is always going to be a negative work, and we're interested in getting the distance that was covered. So that's the reason why we used this, because come to think of it, there's no other way that would have gotten our distance, because we don't have time in the first place. You did have you were given, of course, you were given this, the mass, the mu, and the final and the initial velocity, but there was no time, and we're moving in the what? We're moving in the x-axis. You would have to get acceleration and time. But the only reason why we use the g is because of the weight to get the normal force. But this whole movement is happening in the x-axis, so we cannot use g. You don't have a and you don't have t. No wonder we had to use the work energy theorem to get our distance. Yeah, so however you do it, you notice them, they are saying it's roughly what? To the nearest 10, meaning it's what? Yeah, it's 40. That's basically what you have, because I used 9.8. Yeah, so any questions, guys, here? Is this okay? Any questions? Okay, let me try to give you something here that will be a bit so maybe I should mention something about power. So power, we said power is equal to work over time. The part that I've skipped here for conservation of energy is almost the same as the work energy theorem. It's just slightly different, and I'm skipping it. Yeah, we encounter it in your tutorial sheets. So I want the application here? Oh no, so here. Okay, something like this. So they were just saying, calculate the average power required to raise a 150 kilogram drum to a height of this in a time of 60. So you know to say power is equal to the work done over time. The only work that was done here is force times distance over time. The force that this thing is going to have is its weight. So we're just going to multiply this. So you're going to have 150 times the g, which is simply 10. I'm using 10, then times the distance, which is what? The distance is also 20, then divide the time by 60. We're trying to get the power, by the way. So I've just used the same equation for power is equal to force times distance over time. So the force is simply the weight. This is the weight. the 150 times 10, that's the weight. The distance that we're covering is the height, which is 20, then divided by 60. So if you punch this, so here it's just formulas really, it's very simple. We're just saying 150, then times a 10, then times a 20, then we divide this, so we're going to divide this by 60. This is 500, that's what we are getting. So then they are getting 490 because they use 9.8 when it comes to getting the weight. Yeah, so the weight here, the weight for them, they didn't use a 10, so that's a reason why they're getting a 490. Yeah, but as we are getting a 500 because we used 10 instead of 9.8. Yeah, so hope this is okay. Maybe there's a question I was hoping to find. Okay, no, this is just it. Let me just see here if I can make up a question. Okay, so let me just see if you guys can attempt this. This is a question here. So they want us to get the work done. What is the overall work done on this object? Which is going down, so it's decelerating down. So meaning this is the winning force and this is the losing force. So you have to get the frictional force. Then once you're able to get that, you also get the work done by this force. Then you subtract these two works. That will be the net work. Yeah, so that's a hint. So you can just, someone can just take a screenshot and send this in the group. Our lesson ends here. The next session is going to be linear momentum.